Okay, today is the day of detail, and it's the fine details that the geometry of the wave interference is giving us to make a coordinate system in both space and time and frequency wave number. So we're going to be completing this graph right here that we started already, and as I just said, if you don't have one, please take it now. And we will make use of some of the cute little formulas that came up yesterday involving the rapidity, the exponential of the rapidity, which are Doppler shifts, the velocity parameter for special relativity, the thing that is pretty much standard in all of the relativity texts, with the exception of one that we'll be mentioning at the very end. Beta is called the relativity parameter, meaning velocity divided by the speed of light. In particular, the velocity of, in this case, Alice relative to Bob, or something like that. And then there's a rapidity that goes with it, and it's a hyperbolic tangent of that that gives the this old parameter, and that is the group velocity divided by c as well. So this is stuff that was discussed in the slide from lecture 24, and was the one that asked what would happen to Bob and being attacked from both sides by lasers of different frequencies. Right laser with frequency omega r, a left laser with frequency omega L. And the pretty much all of the theory we need comes from just answering those questions there, and the formulas that come are going to be used here to make our construction. So the first 4 or 5 steps of this construction will be treated right away here. Now we're going to be spending our time pretty much with something that has a Doppler shift of 2 or redshift of 1/2. These are always reciprocal of each other. And that gives you a relativity parameter that is a group velocity of 3/5 the speed of light. So we'll be mostly concentrating on that one. But that's the one I call the faster. Your homework to do on your own is one that has a 4/5 the speed of light. And that's really getting up there. But we'll compare a fast one with slow one. Well, slower. These are all horrendously fast. We don't have anybody, any human or even a animal that has been going anywhere near these speeds relative to the Earth. Mostly this is stuff for particle physics and things like that. But the understanding of how things go at whatever speed is allowed is coming out of this. We'll also be, at this point, introducing something really old, 600 BCE, and it is based on the formula that's at the very bottom of the thing that we worked out last time, namely the geometrical mean. So one of the first jobs for Bob getting 2 frequencies, one forward, one backward, is to take the geometrical mean. That's the what we might call the rest frame frequency, the frequency that he will experience if he can get the right speed to catch up with these 2 people that are making 600 terahertz light, and that's the 600 terahertz that shows up in that geometrical mean. So most of our geometry is pretty much based on just that little piece there, and geometrical mean is a concept that was first talked about way back then. By the way, Thales of Miletus was apparently the first to predict an eclipse, and in terms of human achievement, that is a major thing to be able to do when all you had was superstition about what was going on in the sky or on Earth. So some people credit him with the beginning of really critical mathematical thinking, and he proved that he could do it by doing that. So we'll go through the construction today of 3/5, and then we're going to talk about how to read the graphs we're making. That's going to be the next lecture, is actually use these graphs to do some cool relativistic problems. And we'll take a whole nother viewpoint, mostly space and time, when we do that. But before we do that, I want to show some interesting things that often people find very paradoxical. In fact, people that don't learn relativity in any depth, but just think about it for a while, they come to say, how can that possibly be? This is crazy. Those physicists don't know what they're doing. So I'm going to frame one of it as a he said, she said. He'll be Bob, she'll be Allison, and Carla. And that's sort of an interesting way to look at it in a sort of anthropomorphic way. But also it sheds light on what's really going on here. And that's really an amazing wave mechanics. Finally, with all of the things that are changing here, the rest of this lecture and parts of the next will be devoted to something that doesn't change at all, something that's really invariant no matter how fast you go. Well, we know the speed of light is one of those things, but there's some mathematical concepts and things that come up. And the geometrical construction of a hyperbola, that's really important. And that's one of the things we're going to do almost right away here. Okay, so let's go ahead and begin. And I'll again try to keep these things more or less in sync so that we have two views of whatever we're doing usually, sometimes one of them animating. The first thing I want to do is make sure you have a piece of graph paper and have maybe marked on it where the 600 terahertz lasers are. So this would be Alice's laser here, shooting light in the rightward direction, and then Carla's laser, also 600 terahertz. So the units here in this particular graph, and the one that we'll make to start with, has 300 terahertz frequency units. And then CK is also frequency units, so we're just using the same units, as is a good thing to do if you're going to be doing geometry. So the first step in this that we did last time already was say, I want a Doppler shift of 2, okay, or blue shift factor. And the blue shift factor, in terms of the right and left, is the square root of the thing on the right divided by the thing on the left. So we're talking about a blue shift factor of 1 octave. We're talking about a frequency shift of 2 from 600 terahertz to 1200, from 2 units of frequency to 4 units. So that's the diagram in per space time of this cartoon showing Alice putting Bob's eyes out with UV light on the coming from the left. And then Carla's frequency that Bob is seeing is the red shift that he's either running, if you want to look at it from their point of view, you're running away from this laser and getting the frequency red shifted down by the same factor to here, while the other one has gone the other way. Now, this particular red shift and blue shift are given by ratios, but square root of the ratio, because compared to this frequency, this one is 4 times bigger. And you take the square root of that to get the actual shift relative to the resting frequency. Okay, and what we need in order to build the group wave paths and the phase wave paths are the half sum and half difference, respectively, of the vector. So we're going to start with group vector here with no slope, and a phase vector here with infinite slope, which is what you get with a standing wave, which that's what the Alice and Carla have in their system, in their frame. And we go from this to that, which means that I have to take the half sum and half difference of those two vectors. So presumably, if you have not gotten this particular graph right here, and I'm particularly interested in this vector right here, which is the same as this vector, the group vector, that's the one that you can actually see in the physical experiments that involve quantum mechanical versions of what we're doing here. And then the phase is the thing that's sort of behind the scenes. We indicate phase things with sort of a middle dark blue, and we'll use sort of a grass green color for the group. Okay, now one other thing, and that is remind you that we have the kind of quantities that we use when we actually are doing trigonometry with the phasors and phases of these waves. That is, k and omega are each 2 pi times, these things are just numbers of something, say number of waves per meter and number of waves per second, nu and kappa. And this is actually a Greek U. It's Omicron, but that's what it really is, I think, is a Greek U. So you have your choice. Either use nu, which is a Greek letter that sort of stands with N in our alphabet, but the darn symbol looks too much like a V, so I've switched over and used the Omicron symbol for a number per second. And then a number per meter is a Greek kappa. Okay, and each time 2 pi for phase and group, and the original frequencies, A for Alice, or we also use the letter E for equal frequencies. That frame in which the two light beams achieve equality. Okay, let's see if there's something else here. Yes, the equality frequency is the square root of the product. This is the square root of difference. This is the actual shift between the Doppler blue light and the original frequency omega E. Okay, in this case, we're talking about 2 units here at 600 terahertz. So omega E, same as omega Alice, but also Carla has her laser too. Now, the two things that we're interested in for these two vectors is the half sum, in this case the frequency of the phase, is the half sum of the right and the left. Okay, that's 4 plus 1 over 2. All right, we have 5 halves, or 2.5, as this distance right here. Okay, is that clear? And that is omega E, that's 2, times the hyperbolic cosine. Okay. That hyperbolic cosine being the half sum and half difference of exponential and its reciprocal. And then the difference between those, the half difference here, 4 minus 1 over 2 is 3 halves. 3 halves is this right here. There's 1 unit and 1 1/2. Okay? Meanwhile, the kappas, which I'm not going to write up here, also half sum and half difference. So while this is the hyperbolic cosine making the altitude of this vector right here, this is the same as this. That is, this is a hyperbolic sine across this way. and this is a hyperbolic sign vertically for the g. Okay, and we've already said this once about these particular vectors, but it bears mentioning again. So omega phase 2.5, that's this distance. Omega group 3/2, 1.5, is that distance. Okay, and it takes 2 units to bring the cosine and sine up to the actual things that we are plotting there. Okay, so this is where we stood a day or so ago, or the last lecture. Okay, and there's the hyperbolic cosine, 5/4, the hyperbolic sine, 3/4. Down here, the kappa of the group, okay, we're talking about there is hyperbolic cosine again, this time kappa group over the equality kappa or Alice kappa. That is the hyperbolic cosine right there. So that distance, 2.5, that's this thing right here, is the hyperbolic cosine, just like this distance. Okay. Now there's the reciprocal, which we're going to make a fuss about. So this will be the first new piece of a construction. We might as well do it now and just leave it there, and we'll talk about it later. But the reciprocal of the hyperbolic cosine, the sec, how do you pronounce hyperbolic secant quickly? Just the flip of this from 5/4 to 4/5 is this. Now these two are the famous name coefficients. This one is associated with the Einstein time dilation. This one with the Lorentz space contraction. And that's the end of relativity for many people that are taking it just in the usual university setting. But that's this distance right here. And we need to understand why that distance is what we say. And we'll get to that later on. In any case, it might not hurt to go ahead and draw it on the graph, since it's so important. And this is a mechanical shrinkage of length, and we really need to wrestle with that whole concept. But the basic idea is there's a line going through the tip of the group vector. And that's the one I want you to draw. And my ruler's too short to do that. It must have been Lorentz contracted. I'll put up here a bigger ruler and just draw a line between the tip of the ultraviolet vector, the 1200 terahertz thing that Alice has made happen at Bob's location by coming at him with a 600 terahertz at 3/5 speed of light. So I'm going to go ahead and just draw either a solid or a dashed line. And we're going to be using dashed lines for most of the descriptions in on the screen there of tracks of phases, phase geometry. But what you should get if you do draw this line fairly carefully is something that is a length 80% of what it used to be. That is, it should be at 0.8 if this were 1, or 1.6 if the 1 is over here. And that is the situation here. So this should come down and hit at 1.6 on the horizontal abscissal axis. Okay? Now this line right here and this line right here are tracks on this per space-time graph. They're analogous to similar tracks that will be group tracks on the space-time diagram. So we're really making both of these, except for color, identical graphs for per space-time and space-time, provided we scale each of them properly. And we've already gone through a very detailed description of that scaling for one of the homework problems. So we're going to find shortcuts to that today. Okay, so far so good. All right. Now, before we do any more construction, I want to actually show you an animation of fast and slow. We'll start with slow motion. And I also, and this is, I think, really important, the backwards and forwards of relativity. The thing that I would like you to see is this: what it would look like if you turned it the other way. Instead of the group vector being here and the phase vector being here, going the other way, it opens this way. And just to give you some feeling for that, we have an app that kind of that shows this fairly well. Let's just start here without the graph that it contains, the Minkowski grid, but just a little app that's available in Relativity under per space per time. There's quite a bunch of different topics here, which we'll be going through as we work this out. And then this right here is some different choices of what you want to show. But if you do the right click or control click, you can put up a little screen that lets you show different things. For example, right here, I'm able to pick whether I'm going to see the group and the phase vectors. If I didn't want to see those, I could just not show them, or show only the shifted ones. I'm doing both here. The shaded region, that thing right there, the rectangle that is encompassed by ultraviolet and infrared. And then a little piece of light just to show where our eyes can see, to get us feeling for how blind we are for the frequencies we're talking about. And then later on, the hyperbolas can also be drawn there. So just that. And then you get to see what happens if I turn the velocity to some other value, you see. And what's going to happen is you go to the homework that I've asked you to do is you're going to work up into this region. And where you start from is right about there where everything's green. Okay? So that's the center of the little spectrum there is the 600 terahertz green. Approximately. It's actually a much more beautiful color than that. It's more like turquoise. And then as you come over this way, see what happens to the group and the phase vectors? They open up. You see that? Here they close up when we go speed of light toward the speed of, approach the speed of light in the positive direction, but then they open up like this as you go toward the speed of light going to the left. Okay? Just so you can see where these things can be, they're not always on this side, obviously.
Note the blue shift and red shift at the bottom.
And yes, the projection of this, both on the frequency and the K vectors. This is a single CW light, and this one right here, as we make them back to equal again, right about there. Okay? Make sense? You know where this is, you can play around with it. Now, rather than go back and bounce this thing, what I'm going to do here is ask for one Minkowski cell, just to show you where the graph goes on these things. So there's one cell, and now as I work my way first to a standing wave, which gives me good old Cartesian graph paper in space and time. It's the Minkowski graph paper, really. Minkowski, I think is the name. And then as we work our way up to higher and higher speeds, you can see this thing going like that. Let's see something else that we're going to run into today. And I'll start the thing right there and ask for, control clicking here again, ask for hyperbola branches. Particularly interested in frequency. That's the one we're going to construct. I'll just do the plus omega one actually both of them. You could get both of them for a price of one here. And now you see the purpose of that is to contain the Minkowski graph. And let's do it again with plus k, and also a k hyperbola. There's a group hyperbola that goes there too. Between those two, this is the whole idea of relativity right here, is this graph paper gets crushed as we go to faster and faster speeds. This is way over what I'm asking you to do with your 4/5. Right now we're talking about a blue shift of almost 5. We just passed 5 right there, rapidity of 1.6. These are high speeds, okay? Still not modern accelerators, but when accelerators first came out, that would really be good to be able to go that fast with a proton. Okay? All right. Let's get back to the, whoop, don't want to go back to the Finder, I want to go back to the graph. Okay, now this is something we have to really discuss later, but basically when you're talking about a relativity parameter, the linear one, linear velocity, okay, that's UAB. That means, for our notation, this is not something you see in the text, the usual text. Linear velocity Alice relative to Bob. Now that equals to minus the velocity of Bob relative to Alice. That is almost goes without saying, although it does require a little bit of thinking. So the convention is, for the linear velocity, is this is positive if Alice goes left or right, according to Bob. Okay, and of course the other one is negative, they see that Bob sees the reverse. Bob sees right to left negatively according to Alice. Now rapidity requires further discussion, so I'll pass it up for right now, and we'll go on. And also, these are the coefficients, all of the coefficients that we're going to be using for the rest of the course here. And some of them are famous names, and some of them aren't. They've been ignored. They shouldn't be. They're all important for relativistic and quantum mechanics. So that's mainly what we want to do today, is look at these things and see where they are. And we've already looked at them in the sense that we filled out the first row of this table with all of the quantities associated with the phase. This is the heartbeat part, the internal life of the wave. Has these wavelengths, frequency, period, and wave number, waves per meter. You see all of these numbers are important. And there they are, okay? And then the same numbers get used again to take care of the waves that are not going along the phase. It's a space and time now, so these guys are really moving. As we pointed out, they're always faster than light. In fact, they're infinitely fast when you have the equality frame. When you have the rest frame, the phase zeros are going infinitely fast when they go at all. And that we've already talked a little bit about. But the other lines, the ones that are going this way that are slower than light, always slower than light no matter how fast we push this, the group, the green stuff, okay, that's this row right here, okay? And it turns out they use all the same numbers, but not simply. The lambda phase is tau group. The nu phase is kappa group. The tau phase is lambda group, and the kappa phase is nu group. So you have to be careful how you use these numbers, but this whole theory, relativity and quantum mechanics, looked at this level, is incredibly, shall we say, incestuous. It's just very efficient, is what it is. It's beautifully symmetric. So that, I think, is should be, realized at all points. Now, let's take a look at what we would call a slow wave. not 3/5, just 1 lousy fifth, okay, of the speed of light. Of course, this is very, very fast, but not anywhere nearly as fast as we're going to be, 3 times faster in terms of velocity in just a minute here. But I'm going to go ahead and start this animation, and I guess it would be a good idea to get this one up to speed over here so we can kind of compare these two as well as the geometry. So let's go ahead and let this one here run the slow guy, and we'll run the fast one on this one. So basically what I'm going to do is run this thing, but I'm also going to show the construction for it. Now the construction for it is very crowded in here. It's actually really hard to do slow relativity in a graph like this. And we'll see why that is and how that could be changed. It's also very hard to do it when you're approaching the speed of light, but both of those can be, shall we say, linearized in a nice way. In any case, what we want to do when we run that one is get these numbers in the tables and get some feeling for how big they are for the slow case. And then we're going to move on to this one right here, which is our favorite 3/5, okay, which makes that graph there. So one of the things you should notice right away is even with a fifth, the speed of light, okay, in fact even with a tenth, you can easily see that this line that used to be infinitely fast is no longer infinitely fast. This is another first order effect. Doppler is the one that I made a fuss about, saying why did they do relativity without doing Doppler first order first? The same thing is true of simultaneity. You see, this thing is has its future above my hand and its past below it. Whereas in a graph like this of space and time, when I draw a horizontal line, I mean that's the demarcation between past and future for me. For this person, or this would be Alice and Carla, you see, Bob would say, hey, I can see into your past, and over here I can see into your future. And that's the first order. The asimultaneity is to first order. And that's why magnetism is first order in velocity. We'll get to that later on. It's this effect right there, the tipping of these graphs, that gives you magnetism to first order. And in fact, mostly all magnetism is pretty much a first order deal. Right? Now here it's really leaning up, you see, in this one. Okay? But it happens right away. Even with 100th, you could see that this thing was doing something weird. 100's the speed of light. That's when you would already have to worry about a lot of things. Okay, so what I'm going to do here is go ahead and run the slow guy. And let me, for some reason, I have to hold it and click it. That should do it. There we go. Now, what you see are the arrows pointing to the group zeros, which are this way. But there's the phase zeros making the crossbars. They're not going infinitely fast, but it's really going, right? This is 1/5 the speed of light, so they are going 5 times the speed of light right now. That one arrow there is always seen crossing at 5 times the speed of light. The inverse of what the group velocity is doing, which is 1/5 the speed of light. So that's what's making this graph. It's giving you relativity essentially for free. Now, of course, we have to spend some time analyzing it, but that's fine. And then on this one, the phase has slowed down considerably. It's now only 5/3 the speed of light. But the group is a heck of a lot faster. So this is we need to learn about the geometry of this, not just a couple of coefficients that are in there, but really there's 16 things in there, but a lot of them are equal to each other. So that makes it nice, but it also makes it confusing. Okay, any questions about this? This is the phenomena right here that's responsible for relativity and quantum mechanics. This is it. That's what's going on at a deep level. And knowing that makes it easy to understand things that are not so obvious as what's going on here. Okay? All right. For time being, maybe one of the things you should notice is that when you play with this thing, if you want to see another example, for example, 5 against 3 or 2, okay, or 5 against 4, there's a nice one that's kind of neat. That makes a very fine graph, and boy, that face is really clipping there. Okay. Zoom, zoom. All right. The one that we're working with, and I'll just put that right here, 4 and minus 1 is that. And now we're going to do the geometry of that. Okay. Let's go back to the slide that shows this. And in particular, look at the numbers we just looked at. We just take omega L and omega R and do everything arithmetic you can do with it. Half sum, square root of the product. The equality thing is the square root of the product. Okay. Repeat that again. Doesn't hurt. And then the Doppler shifts are the square root of the fractions. Obviously the blue one is when you put the fast one, the big one, the ultraviolet over the infrared. The flip of that is either the minus row, obviously, the Dopplers, the Doppler factors. Okay, and then the ratio of half sum. That means the ratio of the difference to the sum. That's the group velocity. Flip that over and you've got the phase velocity. And then there's the omega group that turns out to be omega E. That's this thing times hyperbolic cosine. Okay, so Doppler red, Doppler blue, and all that. Well, it's a pretty complicated construction. That's why we're going to blow it up and look at it piece by piece. There's a lot going on in there, and that's only half of it, really. So let's get started on that. Now, the thing that makes this really work is that by simply saying that when Bob encounters a 4-unit ultraviolet burning thing coming from one direction and a nice, warm, sort of low-frequency infrared coming from the other, that he needs to run away from this one and toward this one. Running away from this one to bring it down, both in frequency and amplitude. Amplitude also Doppler shifts, but that's another story for another day. And as he's running away from this one, he's coming toward this one, so this one eventually blows up. Well, when he gets done running and finally gets them equal to each other, it'll be right here. Now what is that? That is the resting frequency for this system of two waves. And the way you show that with the Thales geometry is to take your compass and strike an arc from directly below the phase vector, that is, on the altitude line of the phase vector, the pitcher's mound, if you will, which for me is right there, okay? So I'm finding the drawing part of my compass to go right through the pitcher's mound, so to speak, and watch that compass. I'm going to make it a little tighter so it doesn't move on me. It's always harder to do geometry at the blackboard than it is on a piece of paper. But what I'm going to do is I'm going to strike an arc, a circular arc, and find the geometrical mean. That is Thales' construction right there. After he has drawn arcs for the arithmetic mean, which is the half sum, and not only that, but it is going to go down, and if you do it carefully, it should hit the red. It should hit the red right on those. That's pretty good. Better than I usually do on the board here. And then as you go the other way, it should hit the blue. It should hit the blue limit. So, in a nutshell, that is Thales' construction. And remember, we said that this construction was inside the relativistic view of the phasors adding. So basically the idea is if you want to find the geometrical mean by geometry, which is certainly appropriate for this exercise here, you put the two lengths side by side so they sum, and you bisect that distance. Okay? Now, we have graph paper, so we don't have to do that step, but if you did, that's what you would do, is you strike some arcs up here, from here, and from there, and then draw a line that went through a couple of them. Preferably do one down there so you get lots of leverage. In any case, that's what you're getting right here at this point, okay? The arithmetic mean at 5/2 units here, actually it's located here at the difference mean, the half difference, but its length is the average of these two frequencies, 1 and 4. Okay, so arithmetic mean displaced by the difference mean gives me the geometrical mean. That's cool, right? Nice, cool strut. It's centuries old, okay? This guy's an olive oil merchant in Turkey, actually, across from Greece. Greece had not yet taken another 300 years before Euclid and all those guys really get going. He's way ahead of his time, okay? Way ahead when you consider this is the basis for relativity and quantum mechanics here. Fundamental interaction of interfering light. Okay? All right. Well, that's one little piece of geometry that we'd like to have here. But what comes with it is the ability to very quickly construct a hyperbola that goes through here. And that hyperbola has lots of meaning. That is the dispersion function for matter that we'll be looking at. In any case, the way he proved his idea, one of his first ideas, is that the diameter always subtends a right angle to any point on the circle, is that if you just finish drawing that right angle and you have a rectangle inscribed in a circle, so that becomes almost a zero line proof that he's right about that right angle. The other way to do it is to figure out the similar triangles of these two being similar and work out this fact that you get this geometrical mean as well as a right angle. Anyway, that is showing us, and then a couple more pictures here to make it clear that this thing that we're going to be drawing here is obtained by just, we've already drawn one right angle, this isosceles triangle, and there's another one, of course, there, but there's a whole bunch of them. So basically, every time I want to point on this hyperbola, I'm going to just say, well, where do you want to point? Say right here. Well, I'm going to put my compass, this time I'm going to put it right here, and then draw, not a whole arc, because I'll mess up the board, I'll just draw a little ticker right there. I'll just touch the board right there. And then I'll go on to, this one, say right here, set my compass on the pitcher's mound, but don't draw anything until I get right to the line above there, and I'll hit that point there. So that's what I'd like you to do for the next few minutes here on the board, is go ahead and first of all, make sure that this arc is doing what it's supposed to do, and then go on and use lines on your graph paper to find, for example, where on this line right here would I find a point for this hyperbola. Okay, so I put the point down there at the base on that one and rest it against the aluminum here, so it makes it a little bit easier for me. I can't poke anything with this wooden compass, all this metal ceramics here. And then I go over here and I set the compass to that distance, and then I come back here, find that line again, and put a little dot. And you'll notice that that dot is almost exactly, in fact, it looks like it is exactly, on this diagonal of the rectangle that we used to make this thing. So let's see if that's always true. I'm going to go up here to this line and put my compass down on the geometrical mean, 600 terahertz, and come back and put a dot. Oh, it's a little bit above the line. Okay? Let's do it real quick for the line right next to it. Pick up my geometrical mean here, come back to that line, draw another dot. Okay? A little closer to the line, you see. Let's go a couple of steps away from that line by my grid here, okay? I pick up the point, I come back. Oh, now it's really rising off of that line, very obviously, okay? Might as well draw the other one while I'm at it, make a nice hyperbola if I have lots of points close to each other. The one trouble with this is as you set your compass, start to make a smear down at that end. Just do it very lightly and it'll be okay. Okay. Here's this one right here. The line's barely visible, so I'm going to be careful with this one. And I'm also getting to the limit of my compass. I cannot take this hyperbola much further than about there. I'll try one more. I'm out at 3 and a fraction. Yeah, I can reach that. Come back, and that doesn't look like it's right. My compass loose. That's the other thing. You can see whether you made a mistake. If your compass slips or something, you'll see it by having a bunch of dots that are pretty much in a line, and then having one that's lousy, and you can go and do that one over. That looks pretty good, and let's see if it will hold. Yeah, this hyperbola is headed for the buckwheat. Okay, might as well do the other side while we're at it. Here we are back at the pitcher's mound. I'm going next door by a unit or so. See if I can get that onto the and what I'm seeing just a unit or so is it's right on the line. So what we have here, whatever this curve is, this is a tangent line to it. You're seeing that when you go just a couple of units off from there and set the compass to the original pitcher's mound, then come back toward this new pitcher's mound and draw a thing, and it's a dot that's barely above that straight line. Move myself a little bit further, and it will rise just like the others did above that line, noticeably. So here I am with a dot that's very noticeably above the line. And here's another one, and so forth. Okay? So this takes a little bit of time, but this is, have you ever had an easier construction for a hyperbola? They're usually a nuisance because it's the difference between the foci, right? Ellipses you can do because it's a sum and you just take a string, but this is not so usually so easy. But this is really cool that we can make a hyperbola that easy. Okay. Now, one of the things you should notice, and this would be going with another thing that we need to draw here, we need to draw a base circle. A circle that goes directly with the 600 terahertz. I need to draw a circle that goes through that point and goes 600 terahertz out onto the horizontal axis and ends up just below what would be Carla's laser, and then Alice's laser. Whoops, it sagged again. This, I have this circle here. So this circle is going to be part of our construction, and it's worth going and putting that in too. Okay. So there's a main circle for this particular speed, but then there are all the others. Now, once you've set this circle, you should check that when you turn this around and put the compass on the 4, and it's a good check to see if you're in fact getting that, and I see that this 4 is looks like it's a little high. That means this thing is a little lower. I'm not able to actually get quite to the 0 on this one. I have to work a little bit because the bar for 2 is actually sort of erased here. Anyway, that's pretty good. And so if I set the compass now and draw just a little bit of an arc, you'll find that that arc goes through the points that you made on the hyperbola, and until about here, when it'll actually go a little bit above one of those points. But in any case, the idea is that the hyperbola is a mirror image for low velocities to this circle right here. And that has great significance later on. That's why we get away with doing quantum mechanics with Bohr-Schrödinger dispersions, quadratic dispersions like this one. So we don't go very fast. We don't have to worry about the relativistic effects, which are going to be requiring a hyperbola that climbs up the asymptotes of the light baseline, as it were. So this is the asymptote for that hyperbola right here. And these points here, I'm going to just sort of sketch it in a little bit here. This hyperbola right here, and I sort of have to stop right there, and then it rises up also right in here. Not a very good drawing. It's hard to keep the thing from wiggling. But this curve, which is that curve, very nicely drawn there, something that you can do on paper a lot easier than we can do on the blackboard here. This curve is coming up, and it's going to take a long time before it reaches that asymptote, way up there. But this is what determines the mechanics of matter. This curve right here. Now we're really just talking about a box of light. When you fill a box of light with light, it has mass, and that mass is the inverse of the curvature of the dispersion function. That's called the effective mass. And we'll talk all about that later on. That is the basis of quantum mechanics right there. That's the matter wave. We're doing the exact theory of a matter wave with our ruler and compass here. Okay? Any questions? There should be, because this is absolutely weird. Okay. So that's just another picture showing the group and the phase where they are, and this hyperbola, this magic hyperbola, where it is. Okay. Now, the next part of this, and I'm going to go ahead and pause this because as you can see it's out of sync. There is still that sync problem with the, that's one thing. I'm going to put this thing out for the whole world. We don't want have anything in it that's a flaw. Okay, now this dispersion hyperbola, which is a hyperbolic cosine, that's what it really is if you're plotting relative to rapidity. It has a usual equation, square root of something plus something for algebraic, but that's the best way to say it. That's what we want to do. We want to look at the construction steps that go with that. So there's the two circles that we supposedly just drew. The main one for the p vector of this particular speed, and then some others. And it's a heck of a lot easier to do it on graph paper. Particularly in case if you have a drawing program and can use splines and things like that. I have a very crude one of those, so that curve came out better than usual. There's another circle we should draw. This one associated not with the phase vector so much, but as the sign part of the thing, that is the group wave vector. Now, one of the other things I should point out to you is there's another hyperbola over here that goes with the group. So there's a hyperbola to go with the phase. That's kind of the time-like one, but it's really space-like. And then this one is just flip those two expressions for it. Space and time is being taken care of by the two factors in on the wave. But this circle right off of the horizontal direction for this is the same deal, just that I'm only going to draw a circle. I'm not going to try to draw the hyperbola that goes with the group. That's something, if you want extra credit, that's the way to get it. But right here I need a circle that will take care of a bunch of other factors that we have. Now this one, just like the pitcher's mound circle with respect to the horizontal, this one, if everything is working right, should terminate on the two frequencies. That is, it should terminate right here, and it's here looking like it's not. It's a little high, or a little low, I should say. But probably from where you're sitting, you can't see too much of an error there. And then it should do the same thing, respectively, and go through the 300 terahertz line down here. So this is sort of a test. To the extent that you fail this test, it's just the imprecision of your graphs. Okay, I'll go ahead and finish it on the other side just to make it so it looks like we're on the board there. Keep sliding down. I actually don't have a mark. It's halfway. I'm sort of guessing on that, but I'll try to do the best I can. So this should go right through the 300 terahertz, and it kind of looks like it's not too bad. Okay, so it's those two circles that play with each other to make some other stuff. Now, one of the things that is also a test is that these two should intersect on the tangent line to the hyperbola. And I did a pretty good job right there. So there's this double chord arc where the chord of this circle has both arcs intersecting right at the circle, and it should be right at the circle if everything was perfect. Okay? You can see that in this picture right here, the blue circle and then the green circle, both hitting on the tangent line to the hyperbola. Okay? Now there's some other stuff that I have drawn here. I really might have waited before I drew that, but if you come across from the home point, so to speak, the 600 terahertz point with a horizontal line, that is a useful baseline for some important quantities that we're going to be having to deal with. So going from that center, which I didn't mark, but go ahead and put a mark there, since there isn't one on the graph, going across from there is an important baseline. Okay, now that is the radius of the circle, which is a hyperbolic sine. And the hyperbolic sine is a first-order function of the rapidity. The hyperbolic sine is what gives you the elevation of the past-future demarcation. Hyperbolic cosine is quadratic. It starts 1 and then some plus rho squared over 2 as an approximation. But I'd like to have both the lines to the point of the pitcher's mouth. So we'd like to have that vertical line right there. Now that vertical line should intercept, and I didn't do a very good job, at 0.75. It should be a little bit over from that, a little sloppy there. And then this one right here, okay, should be up by the hyperbolic cosine. Okay, so the two of the famous names are right in this neighborhood, and this one is right here. That's the Einstein time dilation. That's the hyperbolic cosine. The other one that we're going to be interested in is this distance right here, okay, at 0.8. This one's at 0.75, 3/4. This one is at 4/5 in fractions for this particular speed. Anyway, that's right here. This one clearly right on the, in terms of this unit, that's 0.75. The unit is 2, so it's 1.5, 3/2, right there. And that's 3/2 divided by this number right here is 3/4. That's the hyperbolic sine right here. Okay, so we're working with this guy here and this guy. We're also interested in that one for the very famous length contraction coefficient. Okay, now this one is weird, and this is where you see real magic. These are not accidents, these crossings. There are some things here that are accidents. Well, not in this one. It's actually pretty accident-free. But if I draw a line through this, tangent to that circle, it will hit right at where a line comes out from the origin to hit this point that I ended my reference on. And it will cross the tangent if everything is working. Okay? So that's one more thing I want. And then this little pointer right here has really some interesting astronomical significance. When you go fast, the vertical light beams lean into the direction you're going. So we'll explain that next time. But that angle right there, and this particular one, is a stellar aberration for this speed of 3/5. If you go 3/5, the whole heavens above you will move by that angle ahead of you, while everything's getting really ultraviolet in front of you. Okay, so what's really magic about this geometry, we're really only taking one space dimension and of course the one time dimension that we get to have, inverse. The other dimensions are also being watched by this construction. Really more than you might expect to get for such a few pieces of the price of a few pieces of chalk. But in any case, where this happens is right at that point there. The crossing of this circle with the base circle. Okay? And that's where we get another tangent. The line here is now tangent to this circle, which is, as we're going to find out, the Lagrangian function. The relativistic Lagrangian function is being plotted by that circle, just as the hyperbola is a plot of the relativistic Hamiltonian. Shouldn't be giving all this away. We should make it more suspenseful. But this is a line that I definitely want to draw, and I'm being a little careless with the thickness of the chalk there. I want to go ahead and draw it all the way to the end there. But that is a very important point. And then the stellar aberration angle, and I'll use an orange piece of chalk for that, will go right at that tangent point to the circle. So I'm going to go ahead and put that one in, at least part of it. I'm going to put part of it in. So I'm going to draw an orange line from here to that tangent point, and then I'm going to go ahead and meet up with the vertical that has the hyperbolic cosine on it. And erase, I overdid it a little bit right there. So that's the point I like to have. Now, go ahead and extend that for other purposes later on, but that is the stellar aberration line. I guess I might as well put a very light piece of it up here and draw a little star at the end of it to indicate that if the North Star was originally overhead, this is where it appears to be now in the sky. And that's the way astronomers told about the velocity of the Earth for a long time. Okay. All right. And we put the letter K on because that's the K vector of the light. It used to be vertical. And it's also the waveguide angle. When you put a waveguide, a microwave guide, say, to work, this is the geometry of it, too. That we have to talk about later on. Well, anyway, I think that's enough for right now. I'm putting that stellar aberration angle here, sort of a tipped over rho. Rho is rapidity for longitudinal. Sigma is a Greek S for stellar. Okay? This is my notation. I don't think you'll find it anywhere else, but that is the basic idea of it. Now the rest of the construction, which I'm going to pass up now since we're almost done for the day. Actually, why not do it? Because we should probably. But the idea of the, this is kind of an interesting thing, is if you, all of these lines here really mean something, and there's another one waiting to be drawn right below the one that I just drew. I'll also draw it in orange because it's connected with the stellar business. This line right here. And then, if I drop this down from here, it'll go right through that tangent point. That is where this line hits a vertical line that goes through that circle tangent crossing right there. Okay, and I'll just draw it from the P vector down to the stellar aberration vector. Okay. Well, that will go through, and it looks like it's pretty much doing that. This is 1.2, so in these units, this is the velocity 3/5 right here. That's the velocity of this thing. That is the hyperbolic tangent, that distance right there. And then this distance also has some meaning too, but not quite as much as these two. So later on, this distance right here is going to be momentum. That's hyperbolic sine. This is going to be the relativity parameter, u over c, group velocity over c. Set c equal to 1, so I don't have to keep repeating it. And then this little thing here that's shaded, I call it Occam's sword. We started this with Occam's razor. This is the result. This sword has all the information you need to study a waveguide at any frequency where it can propagate. So right up to that point, and that's the velocity in this case for this this particular thing. Now let me see if I've got that right. Actually, the velocity is right here. That's 1.2 right there. And then you can go down here, and that's where the circle would intersect drawn up to the stellar line. And further, if you want, if you draw it further, it'll hit the Lorentz contraction point. I suppose we ought to draw that too. See if I've already done that. Yeah, this is the velocity. And then I go across. I have to look at this to remember what it is. I go across to here. And then draw a, let's see, an arc from that point, and it will go to the, I hope I'm not making a horrible blunder here, but I think that's right. I'll make it sort of dotted so that, now if you draw an arc from that, and I'm talking about having come across to this point right here, okay, and with that, if this were a chalkboard, I would do it this way. Draw an arc, and I should hit this particular thing, which is the Lorentz contraction coefficient. Okay. Well, we are a little bit over time. I guess since we're going so fast through the thought universe, time hasn't slowed down for that clock over there. It just slows down sometimes in your head. This is the beginning, and I think you're beginning to see the structure that this has. It's a very grabbable, knowable structure if you spend a little bit of time with it, and that's why I'm asking you to do some exercises that are a little bit challenging. But this one with 4/5, it's just more of the same. It's just you have to be careful because now there's a lot of contraction, a lot of dilation of things that you aren't used to having that happen to. Any comments, questions? Well, there's more to come.